The James Webb Space Telescope cost $10 billion, took 30 years to build, and launched on Christmas Day 2021. Its primary mission is to look further back in time than any instrument in history, observe the first galaxies forming after the Big Bang, and confirm the standard cosmological model that physics has operated on for 60 years. And now it's producing a systematic crisis that the people who built it are still trying to explain. Webb was supposed to find small, dim, chaotic protogalaxies scattered through the early universe, faint embers from the first few 100 million years after creation, forming slowly in the darkness. Instead, it found massive, bright, structured galaxies that look like they've been running for billions of years, in a universe that hadn't been running for billions of years yet. It found a galaxy so distant its light left when the cosmos were 280 million years old, and it looks nothing like models predicted. It found what may be the strongest chemical signal of biological life ever detected beyond Earth. And it found that the universe is expanding at a rate that two independent measurement methods, now both verified by Webb, fundamentally disagree about. With no explanation for why. These aren't fringe claims. They're published results from NASA, ESA, Cambridge, and UCR. This is the telescope doing exactly what it was built to do, and what it's finding is breaking the equations. Here is the full picture. The Lambda-CDM model is the mathematical framework describing how the universe evolved from the Big Bang. Lambda for the cosmological constant, dark energy, the force accelerating expansion. CDM for cold dark matter, the invisible scaffolding around which visible matter clumps into galaxies. The model predicts a specific sequence. The early universe was small, hot, uniform. Over hundreds of millions of years, gravity pulled matter together into the first small structures. Those small structures gradually merged into larger ones. Galaxy formation was slow, progressive, hierarchical, big things built from small components across vast timescales. Webb looked at the early universe and found the opposite. Massive, luminous, structured galaxies appearing 300 to 600 million years after the Big Bang, objects that Lambda-CDM says shouldn't have had enough time to accumulate that much stellar mass or develop that much structural order. Multiple independent teams confirmed the pattern across different survey fields. It wasn't an instrument error. It wasn't a calibration problem. The galaxies are there. Confirmed February 2026, redshift of 14.44, meaning its light has been traveling 13.5 billion years to reach Webb's mirrors. Existing when the universe was 280 million years old. It shows elevated nitrogen abundances, requiring massive stars to have already formed, lived, died, and seeded the surrounding medium with heavy elements. A complete stellar life cycle, in a universe barely old enough to have begun. A 2025 Nature Scientific Reports paper proposed a partial resolution. Some of the brightness anomaly may come from active galactic nuclei, supermassive black holes in the centers of these early galaxies, accreting matter and outshining their stellar populations. That explanation moves the problem, rather than closing it. Because the black holes are also too big. Webb has now documented supermassive black holes in the early universe, some 570 million years after the Big Bang, confirmed by ESA Webb in 2025, that are overmassive relative to their host galaxies. Under standard formation models, black holes grow by accreting material over time. The early universe simply hadn't provided enough time for these objects to reach the observed mass. In April 2026, a UCR team proposed a mechanism, dark matter decay. If dark matter particles can decay into radiation, that released energy could have seeded direct collapse black holes in the early universe, bypassing the normal accretion timeline entirely. Webb's observations of early supermassive black holes are now being used to test whether dark matter decay rates are consistent with what's observed. The model built to describe reality is being revised by the telescope built to confirm it. Webb found galaxies too massive, black holes too large, and a universe-forming structure too fast for the equations that describe it. The telescope cost $10 billion to confirm what we already knew. Here's what it's confirming instead. Subscribe. Things That Shouldn't Exist covers the stories physics hasn't caught up with yet. The universe is expanding. Every galaxy is moving away from every other galaxy, the space between them stretching at a measurable rate, a value called the Hubble constant, expressed in kilometers per second per megaparsec. Two methods exist for measuring it. They should produce the same number, but they don't. Method 1. The cosmic microwave background. The afterglow radiation from 380,000 years after the Big Bang, the oldest light observable. Planck satellite measurements give a Hubble constant of approximately 67 kilometers per second per megaparsec. Method 2. The local distance ladder. measuring distances to nearby galaxies using Cepheid variable stars and Type Ia supernovae as calibrated standard candles, then working outward. This method consistently returns approximately 73 kilometers per second per megaparsec, 67 versus 73. A 9% discrepancy in the most fundamental measurement in cosmology, how fast the universe expands. For years, the assumption was instrument error. The Hubble Space Telescope's Cepheid measurements might be systematically off. Webb was expected to resolve this by providing sharper, more precise distance measurements that would bring the two values into agreement. In 2024, Webb and Hubble published joint results. The local distance ladder measurement held. The Hubble constant from the local method remains at 73. The tension wasn't instrument error. It's real. A December 2025 Keck Observatory study sharpened it further, calling it a nagging puzzle that persists. The ESA Webb official statement uses the word persists twice. One possible explanation: the standard model is incomplete. An unknown component of dark energy, something that changed its behavior at some point in cosmic history, could produce different expansion rates in the early and late universe. Another possibility: new physics at scales the current model doesn't account for. A third: the universe isn't as uniform as Lambda-CDM assumes, and local density variations are biasing local measurements. None of these explanations have been confirmed. The discrepancy remains open, verified by the two most precise space telescopes ever built, pointing at something in the equations that isn't there yet. In April 2025, a Cambridge-led team published Webb observations of K2-18b, an exoplanet 124 light-years from Earth, 8.6 times our planet's mass, orbiting in the habitable zone of its star. Webb detected dimethyl sulfide and dimethyl disulfide in the atmosphere. On Earth, DMS is produced almost exclusively by marine phytoplankton, biological organisms. No known abiotic geological or atmospheric process produces it in the concentrations observed on Earth. The team called it the most promising biosignature signal ever detected outside the solar system. They were careful. Cautious. Not a confirmation, a detection requiring follow-up. The immediate counter-analysis in Nature proposed photochemical processes in a hydrogen-rich atmosphere could produce DMS abiotically at those levels. The response from the Cambridge team: the photochemical model requires conditions that haven't been demonstrated experimentally. The dispute is unresolved because K2-18b is likely a Hycean world, a planet entirely covered by ocean beneath a hydrogen-rich atmosphere. No confirmed Hycean world exists for comparison. Its atmospheric chemistry under stellar irradiation is modeled from first principles rather than observation. The biology hypothesis and the chemistry hypothesis are both technically viable. The data distinguishes between them insufficiently. What's not disputed? Webb detected a molecular signature on a planet 124 light-years away, in the habitable zone of its star, that on Earth is made by living things. That sentence has never been written before in the history of science. Further observations are scheduled. The detection is real. Its origin is the question that current instrumentation can narrow, but not close. Webb launched to answer the biggest questions in cosmology. 3 years of operations have produced confirmations, records, and revisions, and a pattern of anomalies that runs across every scale it observes. Galaxies too massive and too structured for the age of the universe. Black holes too large for the time available. An expansion rate that two independent methods, both now verified by Webb, measure differently with no explanation for the gap. A molecular biosignature on a planet 124 light-years away that on Earth is made by living things. And Jupiter's aurora shifting faster than any known mechanism should allow. The scientists involved aren't claiming the Big Bang didn't happen. Lambda-CDM isn't being discarded. What's happening is more precise. A model built on incomplete information is being stress-tested by an instrument precise enough to find where it breaks. Every anomaly Webb produces is a coordinate, a data point marking where the current understanding stops being accurate. The telescope cost $10 billion and 30 years. What it's returning isn't confirmation. It's a map of the edges. Drop a comment. The Hubble tension is the one that's getting buried in the coverage. Two verified measurements of the same value disagree by 9%, and nobody knows why. That's not a rounding error. That's a crack in the foundation. Next week on Things That Shouldn't Exist, the Voynich manuscript. 1,500 pages. An undeciphered language with confirmed grammatical structure. Botanical illustrations matching no plant species on Earth. A 2026 computational analysis made the hoax hypothesis mathematically untenable. Here is what it actually contains. Subscribe. I'll see you there.